So what I'm going to do is I'm going to talk about the 7 series architecture, and the reason why we want to talk about the 7 series architecture is because the chip we have on the Nexus 4 DDR board is Artrix 7 100T, and Artrix 7 is one of the 7 series subfamilies. Okay. So if you were to just use the core the way it's given, then doesn't matter because it's running. Only if you want to teach something that you want to make modifications to the core, change pipeline, change data path, whatever, then timing can make difference and other resources can be utilized, and for that purpose having a knowledge or background of it would be useful. Okay? And that's the reason why we want to cover this particular topic. So here's the outline what we're going to do. I'm going to talk a little bit about FPGA, how it started and what is FPGA is. So about 30 years ago we started with this FPGA technology. From day one we had two common resources. One is the logic resources and the other one is the interconnect resources. So the logic resources, it used to be in earlier families, were called CLB or configurable logic blocks, in which you would have the lookup table where you can put the combinational logic and the flip-flop so that using that you can do sequential design, right? And since they were distributed everywhere in the chip, designer could actually program it, and the individual blocks, because they are same type of blocks, they can be connected to what is called programmable interconnect. So those two resources were there from day one. And then as the technology evolved, we started introducing memory. So with Vertex series starting, we introduced the memory resources. With Vertex 2 Pro or Vertex 2, we started introducing the multipliers. So these are hard blocks in the chip, and that gave us density and the speed. Okay, so accessing the memory would be much faster if it's in the block memory compared to if it's in the lookup table. Okay. Similarly, multiplication, you can do it in lookup table, but it would be much faster if you use the hard multiply. And then we provided the chip started becoming bigger, skewing was a problem, clock skew. So we provided the global clock buffers and more clocking resources. All right. Through various generations, because of the customer's demand, we also started adding more architectural resources like Ethernet controller, like PCI block. Okay. So and processor. So with Vertex 2 Pro we had PowerPC as a hard IP, okay, and with Zinc we have ARM Cortex A9 processors. Those are hard IPs, right? So 7 series, we have total 4 subfamilies, out of which 3 are FPGAs and 1 is classified as SoC. Okay? FPGA means it does not have hard IP processor IP block. You can put the soft processor like what you are doing here in MIPSfpga as a soft core, you can do that. And then Zinc as the SoC, classified as SoC because it has the processor hard IP block, not only one but it has 2 processors and it has many more peripheral controllers, okay, which we will see towards the end of the module what are those peripherals. And we have 3 FPGA subfamilies, and those are Artrix, Kintex and Vertex. Vertex is the highest performance, most expensive family member. Kintex is balanced, and Artrix is low power, less costly chip. If you compare Spartan 3E or Spartan 6 even with at least board and all that, Artrix has many more resources. So any design that would fit in Spartan 6 can easily fit in Spartan in Artrix 7. Okay, and we have about 5 family members. So they vary in sizes depending on the particular device part that you get, and so that's why you have range in case of like logic cells, block memory, DSP slices, as well as the transceivers and all that. Now transceivers, you don't get those in small parts, you get those in a bigger parts. Okay. And important thing to keep in mind, Artrix supports 3.3 volt IOs and lower. Okay, so you can go even 2.5 and 1.8 volt if you want to. But the good thing about Artrix is if you are taking some off the shelf ICs and putting or components and putting on the board, you do not need level shifter, because if they are 3.3 volt compliant, you can just connect them. If they are 2.5 volt compliant, you can configure them as 2.5. So all IOs are 3.3 volt compatible. In the FPGA, do we have any tri-state buffers within the chip? And answer is no. It gets translated as a multiplexer. Okay. And then Kintex, if you look at it, there are some IOs which are 3.3 volt, but many are 1.8 volt. Okay. So that's how the speed improvement takes place. Okay, in Kintex. So Kintex is we considered balanced. You don't pay too much, but it gives you enough processing power. And then of course Vertex is the highest performance device. And then Zinc is not going to have that many resources as the other subfamilies, simply because portion of the design or silicon is used for Cortex A9 hard IPs. Okay. So you can do a lot of software implementation, and then where you need acceleration, you can move that acceleration into the programmable logic section. So this chart shows you basically the 5 members of Artrix 7. 35T is the smallest, 200T is the biggest, and 100T is the part that we have on Nexus 4 DDR board. Sarah later on towards the end of the day, she's going to show you how to place this or port this design to basis 3, which cost about 50% or half of Nexus 4, right? And that uses 35T, still big enough chip to hold that, plus peripherals. Okay, it just does not have an external RAM. So if you want to do anything with external RAM, then you have to use Nexus 4 DDR board. If you look at inside, you can classify resources as CLB. Okay, and CLBs basically consist of slices. Okay, you have BRAMs. So CLBs are distributed; they are everywhere in the chip. BRAM is considered column based. There may be 2 columns or up to 5 or 6 columns, depending on how big the chip is. Right, and then you have IOs, which are also column based, and then we have CMT, which is a clock management tie. Right, so that basically has the the DCM, what used to be called DCM now is called MMCM, and then PLL. Okay. And then you have the BRAM. Some of the BRAMs can be converted into a FIFO or can be used as a FIFO, so you have FIFO logic. And then you have buff G and DSP processors or DSP slices, which are column based, which can be used for arithmetic and logical functions. Right. And then you have buff IOs and then MGTs, which are transceivers. So let's look at logic resources. So logic resources, if you look at CLB, consist of slices, and those slices, there are 2 slices in each CLB. Right. These slices have what is called carry chain propagate through them, which always runs from bottom of the chip to the top of the chip. Right. Carry chain is a very important resources when you are writing the models for arithmetic and logical functions. Okay. Counters, adder, subtractor. Why? Because all of them requires arithmetic, and so when you do add or subtract operation, that time it uses this carry chain. It will use carry chain. It means tools. Okay. Vivado or ISE will use carry chain if you write the model behaviorally. But if you write the model structurally, that is, you define carry look adder, or if you define ripple carry adder in a structured manner, then it will not use this. It will be slower. Typically what we say, ripple carry adder is slowest compared to carry look adder. However, if you model carry look adder structurally and you model the ripple carry adder behaviorally, it will be faster because it uses this resource which is useful. So, it's important that you write the model correctly. And then anything that goes, so there is a switch matrix that allows you to connect between the slices, and then it will allow you to connect to the adjacent CLBs or CLBs across the chip, and that is through the fabric routing. So within the CLB, you may have two types of slices. One is called slice L and the other one is called slice M. So the slice L is basically will provide you logic functions. It can do only logic functions and that's it. Slice M will allow you to do beside logic functions the memory function as well as shift register function. Okay. So depending on whether you have both slices as slice L, then it's considered CLB LL, or whether it's M and L, then it's considered CLB LM. Do you care in general? You don't care about whether it's CLB LL or CLB LM. Okay. However, if you are working on a design that is really tight in the chip and timing wise it's not meeting, then you look at the report. Report will show you how the paths are, how the data path is constrained or connected and where is it going through, and then this kind of information will be useful. Okay.
Question.
Yes, please.
Where's the report you said in the report file that you're talking about? Where's that file?
Yeah. So where is the report? So when you start Vivado, when you go through say synthesis, under synthesis there will be in Vivado there is a tab called reports. When you select that tab, report tab, there will be synthesis report, okay, and there will be a synthesis summary report both. Similarly, under implementation, still it will be as depending on whether you have executed that process or not, okay, you will have report present or not, but it will be under that. Okay. Later on, when I switch to my machine, I can show it to you. Within the CLB, this is a little bit slice resources view. So you can see that you have lookup tables being implemented here. Then you have carry chain being shown here, right? Then you have multiplexers. Next slide will show that the lookup table is 6 input lookup table. So it means any function that you write, combinational function up to 6 variables will utilize one lookup table. But what if you write a function of 7 variables or 8 variables? Well, those can be implemented into 2 adjacent lookup tables and connected through these multiplexers. Okay, so they are called F7 and F8, and the reason why it's F7 because you are connecting 2 6 lookup table output to make it 7 equivalent, right? And then you connect next level 2 F7s into F8, right? So that's why they are called F7 and F8. And then you have the 4 flip flops here, and then you have 4 additional flip flops or latches. So within the slice you can have up to 8 4 lookup tables and 8 flip flops, okay, or 4 flip flops and 4 latches, right? You can see also that it's a little bit difficult, but to see the output of the lookup table can go straight out as a combinational, or it can go through the flip flops. If you want a sequential design, okay, it would be through these flip flops. The other thing that to keep in mind, this has 8 flip flops. Okay, it means you can have a real you will never run out of flip flop resources if you are creating a sequential design. Okay, you have plenty of them, and we strongly recommend that you do sequential or synchronous design in FPGAs. Okay. Can somebody tell me why not asynchronous design? Because of programmable interconnect. So if you write the model, okay, and you characterize and you said, okay, this can run, this path can run at 100 megahertz, and you have several logic levels, so it's going through combinational path. Then if you make some modification, it may do different place and route, and your timing can be totally off. Okay, and so you don't even have to add another logic level. It's just re-implementation of the model can mess it up. So, always in FPGAs you deal with clocking edges, synchronous design. Okay. The lookup table is 6 input lookup table which has 2 outputs, O6 and O5, and it has 6 inputs. So, 6 input means 6 Boolean variables function can be implemented, and if you are implementing that you will get an output on O6. However, if you have 2 functions of up to 5 variables, same variables, okay, then those 2 functions can be implemented into one lookup table providing you 2 outputs, right, of up to 5 variables. The key thing is the tools will put those 2 functions in one lookup table provided those both functions are of the same Boolean variables. Okay. If they are different even in one, right, then it will put it into 2 different lookup tables. And then the flip flop is basically D type only. So, if you look at older technology 4000 series and 2000s, over there we had the D flip flop as well as T flip flop and JK flops. Okay. Now, there is only D flip flop. If you want to create T flip flop or JK flop, you have to create using the lookup tables, additional feedback. Okay. So, it has D input, it is clock enable, and you have clock, right. So, having clock enable make basically asserting clock enable is where the on the rising edge or on the desired clocking edge will move the D input into the queue, right. And then unlike older technology where you had set and reset 2 separate inputs, we have one input SR input. Okay. And upon through the configuration bit file, it will initially when you set or when you have reset, it will have that actual value initialized to. Right. There are 8 flip flops. However, all those 8 flip flops use the same clock, right. So, it means if you have 2 different sequential block, always block or process block, they are using different clocks and rest of the thing is still same, they will not be placed into one slice, because all the flip flops in the given slice uses same clock, right. And then you can have rising edge or falling edge, but the inversion takes place at the input of the slice, not at the input of the flip flop itself. Okay. So, these are few things you have to consider. So, packing of various resources within slice and within CLB would take place if certain rules are followed. You can use the lookup table as a shift register, right. And so, shift register can be 16 by 1, 16 by 2, 16 by 4 and so on, within this is within a slice, or you can have up to 128 by 1. What is the shift register look like? So, if you go to here, there is a D flip flop, there is a D input which is fed from lookup table. That lookup table now has A1 through A6 input. So, A1 through A5 becomes the multiplexer selector. Okay. One of the other input becomes D, and then you have a clock input, right. You can have the output after 32 clock cycles delayed if you want, or you can have an output at any desired delay number of clock cycles. This resource is very useful for parallel data path synchronization. So, if you have 2 parallel pipelines going and one is executing for so many clock cycles, the other one is executing for the other fewer clock cycles, at the output of those 2 parallel paths, output has to come at the same time. So, how do you delay? In ASIC technology, you are going to put registers of flip flops. Here you are going to use the SRL, okay. And with one SRL you can have up to 32 clock cycles delay. Okay. So, not very efficient resource utilization. Right. So, question is, when you say 32 bits, is several slices are being cascaded together, because in each slice you have only 8 flip flops. No, you do not use those flip flops. The lookup table is used as the SRL.
But lookup table is combinational.
No, remember that slice M? Slice M has the lookup table that can be used as the SRL. So then you can't use that lookup table as a lookup table.
So lookup table is not just combinational, it's combinational plus.
You can visualize as if it's sequential. So the question was, the lookup table is not just combinational, but it's combinational plus something. And yes, it can implement or can act as if it's a sequential. Okay, so you can think of 32 small flip-flop bits connected in cascade form, and you get the 32-bit output here. Okay, so it's 1 bit output either at Q32 or Qn. Very useful for data path synchronization, very useful for DSP application. So if you want your sample coming in, you want to hold it for so many clock cycles before you use it, you can change that here, or you can assign that here. And this is dynamically you can change also. Okay. And then same lookup table in slice M can be used as what is called distributed select rank. Okay, where remember we have 2 outputs of lookup table. So if you use both outputs, then it's 32 by 2 you can get, because 2 to the power 5 is 32 locations. Okay, so 32 by 2 is one configuration possible, or if you use 06 only, then 64 by 1. Right? If you put 2 lookup tables together, it can be 32 by 4. Okay, or you can have 64 by 2, depending on how you are connecting them, whether you are utilizing them in parallel fashion or in sequential fashion. Right? This distributed memory can be configured as single port RAM, which is your input and output, 1 port each. You can have dual port RAM, where you can have 1 read port and you have 1 write port. Okay, 1 read and write, and then 1 read only. You can have simple dual port, which is 1 write only and 1 read only, but they are 2 different ports. And when we say 2 different ports, it means they can be different sizes also. Okay, and then we have quad port, so which is 1 read write port and up to 3 the read only ports. Let's look at I/O resources. So I/O resources wise, we have many I/O pins on the chip, right? And as I mentioned in the earlier slide, they range from anywhere from 1.2 volt to 3.3, right? And so you can configure them to whatever voltage, whatever the standard you want through I/O configuration. So as part of the I/O planning, or as part of post synthesis configuration, or through Xilinx design constraint file, you can say I want LVCMOS 33, or I want say LVCMOS 25. You can configure them. Okay, and so you can do those through the, for various voltages. You can also configure them as a single ended, or you can configure them as differential. And then you can also have reference input. So when you have reference input, you can actually compare with the reference input rather than the bank input, right, which we'll see in the next slide. And then tri-state support. So tri-state is possible for external world, not inside the chip. And then you can use it in differential mode for LVDS type, and then DDR3 compatibility and all that. Okay. So I/O block consists of 2 pins, okay, and 2 subcomponents. One is called electrical resources, the other one is logical resources. In electrical resources, so the 2 pins are subdivided in electrical resources as positive end and negative end. So if you are using differential input or output, the positive should connect to P and negative should connect to N. If you look at the I/O chart of the chip, for each and every pin, the pin mnemonics will have _P and _N. So you should assign the right pin to the right voltages if you are using differential. If you are using single ended, you can use either one or both of them. All right. So the voltage compensation and the I/O standards are implemented right here. Once that happens, then you move into logical side, and then you do logical operations using logical resources. Right? So, this just shows you that you have pins here and it's going into the fabric, or from fabric is coming back out, right. It also has VREF voltage. So, if you are not using VREF and you are using LV-CMOS 33 or 225 whatever, right, standard, it will be treated as logic 0 if the input is near ground, and it will be treated as logic 1 when input is VCCO. So, there are other voltage pins which are, one of them is being VCCO. Okay. You can also have VREF for each bank, and so VREF will basically, if you are using that, then it is reference to that voltage. Okay. So, anything below that voltage is considered logic 0, anything above that is considered logic 1, and then differential is when Vp is less than Vn, then logic 0, otherwise logic 1. So, the logic electrical signal gets converted into logic value, and that logic value will go in and out through what is called the O logic, O delay, I logic, I delay pairs. Okay. If you are using the differential ones, then P will be on the master side and N would be on the slave side, right. Your delays are, you can configure them with 52 picosecond resolution. Okay. So, you can, this is useful when you are doing source synchronous design. You have an external device that is sending the data, it is also sending the clock, one thing. Now, your traces on the board may have different delays. In order to compensate them, you can use O delay or I delay. So, in this case, if it is receiving, it is I delay, if you are sending, it is O delay. Okay. You can also convert serial data into parallel or parallel data into serial. So, that is through O SerDes and I SerDes, right. So, you can write, your design can generate parallel information, write it into a register in the logic in the fabric. From there it can go to O SerDes and it can go serially output. So, you do not need that many pins, 32 pins, if the externally you want to send it serially. So, the device on the outside of the FPGA is able to receive serially, you can use it in this fashion. Memory and DSP-48 resources. So, select RAM or select distributed RAM was considered the first level of hierarchy, memory hierarchy. We have support 3 level of memory hierarchy. Second level of hierarchy is the BRAM, and the third level of hierarchy is external memory to the FPGA, okay, for which you need a controller, right. So, the block memory can be configured as single port, dual port, or true dual port. Okay. So, the dual port block memory would look like you have 2 different ports with individual clock signal, clock enable signal, write enable signal, and output enable signal. Okay. Addresses and data input port and data output port, they will have their own. Okay. They can run at different clock speed, they can run at different width. So, port A, for example, can be at 4-bit input and you may be reading 8-bit output on port B, okay, or 32-bit output, because internally it uses the same core, memory core, it just internal address would be different. Okay. It is every bit or every other bit or every 4th bit for 1 bit, I mean every location, or twice the word size, or 4 times the word size. It has to be power of 2. You can also use this BRAM as a FIFO. So, they are 36 kilobit memory, can be configured as 1 bit wide, 2 bit wide, 4 bit wide, 8 bit wide, 9 bit, 18 bit, 16 bit, up 32 bit, and so on. Okay. You can use 36 kilobit BRAM as an 18 kilobit BRAM and 18 kilobit BRAM or FIFO. So, when would you use this? When you have small amount of data which does not require more than 18 kilobit, then in order for you to utilize block memory in more efficient way, you would use it into 8 kilobit VRAMs or FIFOs. Okay? And then it's byte write enabled. So, it means on each VRAM you can have up to 4 byte enables or write enables. It means you can implement 32-bit bus using one VRAM. You can have 32-bit wide and 8-bit byte, because many processors are all byte oriented. Okay. So, byte, this is something that we have introduced since Vertex 5. Before Vertex 5 it was single, and so then the efficient use was not possible. And then DSP-48 slice, something that is useful for arithmetic logical functions, for floating point operations and so on. So, many of our floating point cores now that you will find are using DSP-48 slices. Okay. It consists of 25 by 18 as the multiplier. So, when hard multiplier or hard DSP was introduced in Vertex 2 Pro, okay, starting with Vertex 2 Pro, they were 18 by 18, but now it has been enhanced to 25 by 18. Okay. Then it has multiplexers, so you can get a multiplier output, you can get straight output from this B path or A path, or you can have straight from D or C path. Okay. These are various input ports you have. They are 18 bit, 30 bits, 25 bits, 48 bits. So, when you want to cascade to adjacent DSP-48 slices, output of this 48 slice can go into as an input of C. Right. This is saying it's doing addition, subtraction and logical functions, right, arithmetic and logical functions. You can cascade the partial product back into through PC in. So, you can do the accumulation using the one DSP-48 slice until you get out, or you go out of 48 bit requirement, right. Also, these are you can change the data path or the operation itself every clock cycle, and that is through what is called op mode bits. And op mode bits have flip flops here, so you can actually provide or change the execution or operation every clock cycle, and the effect will take place in the next clock cycle. Okay. XADC, we have with 7 series, every part will have the XADC, which stands for Xilinx A to D converter. It is a 12-bit A to D converter. It has up to 17 analog external inputs and also has 3 on-chip inputs that we will see in the next slide. Important thing is it's 1 volt input range, 1 mega sample per second is the processing time, conversion time, and 12-bit. There are 2 A to D converters. Okay. So, here is the block diagram where it shows that you have 2 A to D converters, you have multiplexers, you have on-chip sensors, and you have 17 external analog inputs. So, one can in design environment can say, are my voltages to various banks, internal voltage, is it going out of range? Is it getting too hot, or has the voltage dropped? So, you can sense the temperature, you can sense the voltages through these on-chip sensors and create an interrupt or alert, so that system can take the corrective action. So, and conversion takes through A to D converter, and then conversion output can be accessed through the data register, conversion control configurations, and status registers will allow you to monitor whether conversion is complete or is in process. Clocking resources, basically we have the a large amount of clock buffers. So, we have global clock buffers, we have low skew clock buffers, and this can handle the clock fan out. So, minimizing the clock skew because the chip is becoming bigger. They are divided according to regions. Each clock region is 50 CLB tall, okay, and spans half this chip. And then the CMT, as I mentioned before, consists of MMCM and it consists of PLL. So, PLL will allow you, if so, the clocking wizard will automatically use either the clocking manager or PLL as the first stage, followed by the second one, depending on your input, clock input, how good it is, how bad it is, So if you want to filter out jitters, it will use PLL first, and then if you have multiple output that you want to generate, it will use MMCM for that. Okay? And it will also allow you to create various clock frequencies. So in MIPS FPGA, the clock source is 100 megahertz, but the entire system is working at 62 megahertz. The Xilinx SoC, basically the Xilinx family consists of the programmable logic, which is yellow section, and the blue or gray here is the processor section, okay, or processor system subsystem. So processor subsystem consists of dual Cortex A9. Each Cortex A9 has this 32 kilobyte of level 1 cache for both instruction and data. It also has 512 kilobyte unified L2 level cache. It also has a Snoop controller, triple timer counter, interrupt controller, DMA engine, and so on. Beside that, it has bunch of peripherals, okay, like CAN controller, the SPI controller, I2C, and so on, and USB controller. So you can connect Ethernet port to this port, and it can start working. Very important thing to keep in mind. Xilinx is processor first, programmable logic second, booting. Okay? So as you power it on, this block will be working, unlike the PowerPC based architecture where we had to configure the FPGA before we could use the PowerPC. Okay? And then you have the input outputs, which can go to the dedicated pins. So if they are dedicated pins, then you do not require to give constraint files, okay, or constraints for those pins. The tools will pick it up. If you are using user I/O pins, you must provide the constraints, otherwise it will give you error. Right? The PL section will have IPs, various IPs, and PL for programmable logic, and the CPU can talk to the PL section IPs through various ports here. Okay? And so this just shows you that you have two subsystems, and you have two different. There are 7 family members. The smallest three ones uses Artrix based, okay, whereas the bigger 4 ones uses Xilinx based. Xilinx based means it has the high performance as well as some IOs which are high range, which is 3.3 volt. In case of Artrix, it's all are high range compatible. Right? Okay.